Hi everyone, welcome to my channel. If you're new to this channel, kindly subscribe and hit that notification button to always get my updates. In this tutorial, I'll talk about something to do with computational physics and how we can solve different problems using Python. And in particular, I'll talk about the SymPy Python library. SymPy Python library is basically a Python library that handles all the symbols, all the computations related to do with the symbols. All right, so if you want to deal with anything to do with symbols, by first of all defining all your symbols, all your variables, and then perform your computations, SymPy is the Python library that can handle that. So basically, let's begin by looking at how we can install SymPy. All right, so how to install SymPy is simple. We just need to use the pip command in the cmd window, and then we can then further say pip install SymPy, as simple as that. Then we can have our SymPy library installed on our computer. If you want to do that in Anaconda, you can just simply make a command, conda install SymPy, as simple as that, and then it will be fully installed on your computer. All right, so now I'm assuming now you are done with the installation of the SymPy. Let's look at how we can define variables in SymPy. Okay, so to do this, we need to call some functions and some methods, as we are going to see. So let's get down to that. So first of all, we need to import SymPy library as usual, so to prepare our workbook or notebook. So I'm going in this case to be general and call everything related to do with SymPy, all the modules and all the functions within the SymPy library and all the packages. So to do that, I'm simply going to say from SymPy, since it's already now installed, import star. So star simply imports all the packages, all the modules, and all the functions within SymPy. In order to get a good idea about what is all within SymPy, we can just simply call help, and then we can then know what is all within SymPy. So now my SymPy is imported within this notebook. Let's first of all try to check what is within SymPy. So I'm going to say help SymPy, and if I run that, that will give me all everything that is related to SymPy. So we have the package contents, ABC, algebras, assumption, benchmarks, calculus, and so on. We have geometry, we have logic, we have matrices, we have plottings, we have sets, and we have a lot. So when you go down again, you have sub modules that are within the SymPy: add, array, basic, cache, common, and so on. All right, so you can go through this and convince yourself and what we have all in SymPy. We have symbols that handles the symbols. We have equations and so on. So I can leave it here, and then you can try to convince yourself what is all within this library. So now that SymPy is imported in our notebook, let's try to look at how we can define variables within our workbook. Okay, so to do that, I'm simply going to choose my variables of choice. So I can say I need variables to so let's begin by choosing variables. Okay, So I'm going to choose x, y, and then z as my variables. Okay, and I'm going to accompany that with a function called symbols. Okay, and then I'm going to mention those variables or the symbols I want to use inside. That is x, y, and then the z. Okay, so when I enter that, I'm going to have all my x, y, z now defined. So this means that I can now go ahead and write anything to do with x, y, and z as a variable or as a symbol. Alright, now that we have our expression as x plus y minus z, let's go ahead down here and mention, let's try to print or just call what is our expre and see what we come up with. When we do that, we come up with x plus y minus z. As simple as that as we have it. It's just an expression. Alright, so now let's assume we want to substitute for some of the those symbols, like let's say x equals 10. Okay, so the way to do that, we are going to call back our object representing that expression, which is xpr. Okay, and then we use the dot subs command method. So we, for substituting, we use the dot sums method. How it works is that you mention the symbol you want to substitute for and what you want to substitute it with. Okay, so in this expression, I will say expression dot subs. Okay, and I want to only substitute for x, so I'm going to say x and then substituting it with 10. To be specific, let's go ahead and print this. Okay, so I'm going to print the expression substituted with that, and let's see what we get. What we get is amazing in such a way that it has replaced x with 10. Okay, now one thing I want you to note here is that if you call back expre and see what we get, okay, it will take you back to the original function. So that's the beauty of this method dot sums, in that it doesn't change the original expression. It remains as it is. Okay, so if you want to just create another expression, then we would say, for example, expre 1. Okay, the original one is just expre, and then we have that being equal to our expression here, right here, which we have tampered with, and that will give us another new expression called expre 1. So when I do that and call back expre 1, if I call it, then that will automatically give me the new substitution we have as y minus z plus 10. Okay, so that's how you can play with the substitution. So now let's try to look at if we are substituting for all symbols. How do we go about that? All right, so in that case, we can create our another object which I can call answer, and I'm going to say that from this expre, which is the original, I'm substituting again x as, I have to comment on this, x as 10. All right, and then y as maybe 1, and then z as 1. So notice that the y and z will cancel depending on my numbers I've set, and then our answer is going to be just 10. So in that case, I'm going to say dot subs. Okay, and I'm substituting x with 10 as before. Then I need to continue with this as dot subs. Okay, y, substituting it with 1, and then finally with dot subs. Okay, and then the z or the z substituted with 1. Okay, and my answer, if I run this and call back my answer, this has to give me a 10 as the answer, simply because y is 1, z is 1, so our balance is just 10 in that. So this is the beauty of, or how you can play with expressions, substituting them with or if you have a given equation you want to solve, this is how you can play with it. Write the general equation as it is and then begin your substitutions as we normally do in science or in physics. Just first of all, not write down your equation. Let's say it's a projectile equation or it's a certain energy equation, and then finally you list down what you want to substitute with, and then go ahead and do your computation of that expression. So with that said, let's try to move further and try to look at how we can define more complicated expressions. The symbols is already imported within our one workbook or workspace. I'm just going to go ahead and list some new symbols I'm going to use. That is A, B, C, D. Okay, and then these ones are defined again as my symbols, new symbols, and inside I have to put them inside the quotation A, B, C, and D. Okay, these are my new symbols that I'm going to work with. So to do that further, to complicate the stuff, I'm going to write my EQ as my equation or my expression, just to be exact. Let's call it EX as our expression, and our expression is going to be equal to A squared plus B squared using the double star. So when we go down, I can call back the EX, and that will give me A squared plus B squared as our expression. Now let's try to complicate the matter one more time. I'm going to define my other variable C, which we already have as a symbol, as being equal to the square root of A cubed. Okay, A cubed plus the inverse squared of D. Okay, so that is 1 over D squared. Okay, D squared. I can change this slightly, maybe to cubed, to make my point a little bit clear and interesting. So we have A squared plus B squared. So now we have defined as well our variable, new other variable in terms of symbols, C, as being equal to another expression, which is A cubed plus 1 over D squared. Now let's go back in our EX expression and do some substitution. So I'm going to say this dot EX dot subs. Okay, and this time I'm going to substitute for B. B is going to be substituted with C, which C is up here. By the way, I would also print out C and we see how it looks like. This is how it would look like, C itself. Okay, so now that is the expression I'm going to substitute for B, and we have already our simple code here for substituting. So if I run that, this is what we are going to have. So it looks beautiful, very nice, and this is just A squared plus, where we have B as cubed. Now we have substituted this whole expression, which is of the square root, and now because this is power cubed, then this becomes 3 over 2, as simple as that. Now let's say I wanted to substitute for some of those variables within this expression. Then I'll go ahead and substitute for some of these. Since my final expression, let's call it EX2 or just EX1. All right, and this is equal the equivalency of this expression EX dot subs BC, and I'm going to just keep it just there within EX1. Now let's try to substitute for we know now it is in A and D only, so let's try to substitute for some of those symbols A and D. So I'm going to say EX dot sums. I'm going to begin with A. A is going to be substituted with 2, All right, and then dot subs substituted d substituted with 1. If you can look at that quickly, a is just 2 and this is going to be 4, and then inside here we have a cubed is 8 plus 1, that's 9. 9 power 3 over 2, there's a square root of 9 that goes to 3, and 3 cubed is just 27. 27 plus this outside 4, that goes to 31. So that means that's the answer we need to expect to get in EX1. So if I run that, that will give me automatically 31. So you can see that our substitution works pretty well in the simplest way. So now let's run to another main component of this tutorial, and that is defining equations using SymPy. Okay, so let's see how we can define now generally equation which can be quadratic or anything. So to do that, let's see what we all need to do to import. So basically I have already some of the packages or some of the functions imported in my workbook, but I will just try to import them again. So I can say from SymPy import symbols. This is already imported, but I'll just, for demonstrative purposes, I'll repeat it again. I'll need also EQ that is going to handle the objects of the equations, and then we need also the solve function. All right, we can try to look at the equations that we are going to solve. The equations that I feel that they're easy to look at, I have 2x plus y, this is equal to 5. Okay, and then we have also another equation that I feel is also simple to just memorize in the head, x minus y equals 1. Okay, and I need to solve these ones with SymPy and C. So let's just try to have this. These are the equations we are going to solve. Now we need to go further and try to write our equation object. So how are we going to do that? We can begin by writing EQ1 is equal to, we will make a use of EQ, which is already imported, that creates this equation object. So we have EQ, and then from each of these equations, all the items have to be taken on one side. And so in this, I mean we have 2 times x plus y, okay, minus 5. That means on the other side we have left 0. And the same thing we are going to do for equation object 2, and this is going to be equal to EQ, and everything which is x minus y now minus 1. That means the other side we have 0, and these are our 2 equation objects that we need to work with. Okay, so it's complaining here, but yeah, so it was complaining before because I had not rerun this one. So now this is what we have. So we have EQ1 and our EQ2. Now the thing is, now the goal is now to solve these equations. Okay, so how do we solve these equations? We are going to solve these equations using the solve command. Okay, and let's see how to do that. So we will create another object that will swallow all those solutions. So I'll call that solution, and this is equal to the command or the function that is solve. Okay, solve what? We need to put our equations, the equation 1 and equation 2, in form of a tuple inside this function, and also the variables that we are going that within this equation as also a tuple. So within, I mean, we have EQ1, okay, comma EQ2, and this is a tuple of the equations, and then this is a tuple of the variables x and y. And so when we do that and we have our solution down here and we run this, it's going to return for us x is mapped to 2 and y is mapped to 1 in form of a dictionary. All right, so we can go ahead further to print out the individual solutions of both x and y. To do this, we can just use a simple format command. So I'll just print out my solutions and say the solutions are x equals, so I can put this in brackets. Okay, x equals that and y equals this. Okay, but what's the equivalence of each of the x's? So then I go to my format command. My format is that x is on solution is within the solution for x, so that is for x, and then the next one, the next solution is on solution within the y. That's what I need. Okay, so let's see if we run this below what we are going to get. We are getting the solutions are x equals 2 and y equals 1. So this gives us a good understanding of how we can use the SymPy first of all substitute for expressions, to solve for simple equations and write the expressions themselves and equations themselves, and finally and how we can solve equations simultaneously. Please, thanks for watching. Kindly subscribe on my channel, share my links to spread the knowledge, because knowledge is power. Okay.